So, in this lecture we will continue with the exercise of solving a few problems, and since this being the last lecture in this series, we will take a look at what we have done in this course and also see what else could be done with this background, where you can move on if you have understood this course. So, we will begin by considering a problem in random vibration. A single degree of freedom system is driven by a filtered Gaussian excitation and is governed by the equation x double dot plus 2 eta omega x dot plus omega square x is equal to f of t, and system starts with some initial conditions, and this excitation f of t is a filtered white noise. That means a white noise xi of t passes through a first order differential equation filter, and this xi of t is 0 mean Gaussian white noise with covariance given by 2d Dirac delta of tau, where tau is the time lag. Now, this problem, the problem is to analyze the response of the system, but we would like to approach this problem using Markov process theory, and the problem is actually to set up the equations for time evolution of first 2 order moments using Markov process approach. Then consider the response in the steady state and evaluate the response moments. So, that is the problem. So, the governing equation is rewritten here, and this is the filter equation, and we introduce a state vector x1, x2, x3, where x1 is x, x2 is the velocity, and x3 is f. So, this is a second order differential equation, the governing system that governs the displacement x, and this is the filter equation. So, we declare the variables from this system, namely displacement and velocity, and this process f of t as the states. So, now we recast this governing differential equation into the state space form. So, x1 dot is x dot is actually x2. So, the first equation is x1 dot is equal to x2. x2 is the velocity, x2 is x dot. Therefore, x2 dot is acceleration. So, x2 dot is for acceleration we go to the governing equation. This is minus 2 eta omega x dot minus omega square x plus f of t, and f of t is x3. And the third equation is x3 dot is equal to minus alpha x3 plus xi of t. Now, we rewrite this in the form of a stochastic differential equation. As we have seen, this is dx1 is x2 dt, dx2 is minus 2 eta omega x2 minus omega square x1 plus x3 dt, and dx3 is minus alpha x3 dbt, where dbt is a increment of Brownian motion process with these properties. You may recall that when we discussed the Markov vector approach for solving random vibration problems, we considered the general form of SDE of this form for a n dimensional response vector, and we showed that the time evolution of expectation of a function of h of x comma t follows this law. So, this we have derived when we discussed the Fokker-Planck equation and the backward Kolmogorov equation and the moment equations. Now, we will use this and derive the required equations for the moments. Now, for the particular case, the form of this equation is, if we compare this form with this standard form, we see that f1 is x2, f2 is this minus 2 eta omega x2 minus omega square x1 plus x3, f3 is minus alpha x3, and this g into dbt is actually dbt. Equipped with that, we can write now the equation for the moment equation, where I will actually substitute for f1, f2, f3 and for this g dg transpose ij, and if I do this for the system under consideration, the moment equation for the expected value of some h of x comma t is given by this. So, if we start by taking h is x1, so expectation of x1 is, if we go back here, it is x2 into dou h by dou x1, dou h by dou x1 is 1, it is expectation of x2. Similarly, if h of x comma t is x2, I get dou h by dou x2 is 1, therefore, I get on the right hand side expectation of minus 2 eta omega x2 minus omega square x1 plus x3. In a similar manner, we can set up the equation for the third element of the state vector. So, these are the equations for the expected values of x1. So, you can quickly notice that these equations are closed in themselves. If you want to find out x1, x2, x3, we need to solve only these equations and we can go ahead. So, suppose if you want to find steady state, here in the steady state, expected value of x2 will be 0 and this RHS will be 0 and expected value of x3 will be 0. So, we can solve these three equations and obtain the steady state values of these moments, and you can show that indeed all these three values, assuming that initial conditions are deterministic. I mean, if we reach steady state, of course, the solutions are independent. It will be possible for us to show that all these three expected values in steady state would be 0. How about the second order moments? So, you start with h being x1 square and x2 square, x3 square, x1 square, x2 square, x3 square, x1 x2, x1 x3, x2 x3, etc. So, we need to go back to the expression for the evolution of h of x comma t according to this equation and substitute. So, we will be able to derive these equations. Again, these equations involve only moments of the second order, they can be considered separately. So, these also can be solved. So, we can use something like Runge-Kutta method or some other predictor corrector method to solve these equations if you are interested in time evolution. If you are interested in only steady state, if we assume that for the initial conditions on these equations have to be specified. So, first let us address that issue. So, if you assume that x0, x0 dot and f of 0 are all deterministic, then it turns out that the initial conditions for the expected values will be corresponding to these respective initial conditions, and then all the second order moments will be 0 at t equal to 0. Now, for the steady state response analysis, we put d by dt or expected value of h of x comma t to be 0, and this equation, which is independent of t now, is the equation for steady state response moments. So, we can write down those equations as I discussed already, and we can write all these equations where right hand sides are around 0, and we can cast this in a matrix form. First, this is the equations for second order moments, and we can show that by inverting this we can get the required values of steady state response moments. Mean I have already shown they are all 0. So, the analysis on mean can be done independent of analysis of second order moments. So, this is a typical property of linear time invariant systems driven by random excitations. So, there is no problem of closing the moments, equations for moments are always closed. So, they are straightforward to handle. Now, this is a problem on simulation of random variables. So, we consider a problem in reliability analysis of a cracked plate. We consider a situation where we are asked to simulate a vector of 6 non-Gaussian random variables. The specification of these random variables is limited to the description of first order probability density functions and the matrix of correlation coefficients. Now, the problem is to develop a simulation procedure based on the Nathau transformation to simulate 5000 samples of the random variables. Estimate the first order probability distribution function from the simulated sample and perform the Kolmogorov-Smirnov test to verify if the simulations have been performed satisfactorily. So, this is the problem. So, the specification of these 6 random variables is x1 is normal, x2 is log normal, x3 is log normal, x4 is exponential, x5 and x6 are jointly normal with mean. The first two things are first two quantities, this is mean sigma 1, mean sigma 2 and correlation coefficient. So, the correlation coefficient matrix except for these entries at this in these rows and columns is diagonal, but rho is still a non-diagonal matrix. So, and also we are say a complete specification of a 6-dimensional non-Gaussian random variables involves specification of 6th order joint density function. So, you must understand that the problem is now to simulate samples from this partially specified description of these 6 random variables. So, if you quickly recall this, I am not going to explain again, this is the reference to the text where we describe the required mathematical tools, that is how to simulate non-Gaussian random variables using Nathav's transformation tools. So, this we have discussed. So, essentially we introduce 2 normal random variables. For example, if we are interested in simulating 2 random variables which are non-Gaussian and which are partially specified, through these 2 transformation we introduce 2 Gaussian random variables with an unknown correlation, and we will calibrate these correlations to match with the correlation of x1 and x2, and we, as we have seen, we need to solve this integral equation. To do that, and I have already explained how to handle this computationally. So, the strategy for the determination of unknown correlation coefficient between those 2 hypothetical Gaussian random variables has been explained. The essential idea here is that the unknown here resides inside the integrand, and what we are left hand side is known. So, what we can start by doing is we can we know that this rho 1 2 and rho 1 2 star are bounded between -1 and +1. So, we can solve this equation for specified values of rho 1 2 star at certain intervals between -1 and +1 and get a idea of behavior of rho 1 2, and from that we can estimate for the required value of rho 1 2 what should be rho 1 2 star. This requires development of a suitable computer program. This is something that cannot be handled on a pen and paper mode. So, you need to write a computer program to do this and to simulate the random numbers, required random numbers. If you are writing your own codes, you should start with simulating uniformly distributed random numbers, apply suitable transformation, Box-Muller or certain transformations, and generate the required random numbers. So, such an exercise has indeed been carried out. So, I am showing some selected results. This is results on the log normal random variable with 5000 samples. Blue line is the simulation, and red line is the target log normal cumulative distribution function, and they seem to agree quite well. We need to perform the Kolmogorov-Smirnov test on these 2 curves using data in these 2 curves and verify whether we can accept the hypothesis that the data originates from a population whose probability distribution is indeed the target log normal probability distribution function. So, this is similar exercise on exponential distribution. Again, to a first look, the simulation looks alright. We can verify this through a proper statistical test. So, this is an intermediate data which you may find useful if you would like to reproduce these results, where this is the correlation coefficient matrix for the equivalent Gaussian random variables which we need to transform using Nathav's method, and this is an intermediate result that you could verify when you implement this procedure. So, in the actual simulation that was performed in this exercise, the simulated mean vector is as shown here and standard deviations are here, and the simulated correlation coefficient matrix it should be here all these entries should be 0 because these are not strictly 0 because of sampling fluctuations, and along the diagonal of course they are 1, and off diagonal here the target value is 0.835, and what has been realized is something pretty much close to that. This is equivalent Gaussian, and this is 8345 instead of 835 is what we are getting through simulation. So, this partial set of results should help you to check if you are doing your calculations right, especially this intermediate step of finding equivalent rho for the Gaussian random variables. We next consider a fairly complicated problem. This is a problem of a 2-degree freedom system which has both cubic and hysteretic nonlinear stiffness characteristics. The springs K1 and K2 here have cubic force displacement characteristics. K3 is an inelastic spring, it has hereditary nonlinear characteristics, and this is modeled using Bouck's method, and P1 and P2 are random excitations, and this R1 and R2 are the reactions. So, the problem is to formulate the equations of motion and recast the equation of motion into a stochastic differential equation, and then numerically simulate samples of response of this system using 1.5 order Taylor's scheme based on theory of stochastic differential equations. So, I will provide you the intermediate steps. This again is an exercise that can only be done through a computer program, and you need to develop the program to be able to solve this problem. So, the Gowning equation here for u1 and u2 can be written here. As you can see, K1 this K1 u1 plus alpha 1 u1 cube is the cubic stiffness, and K2 is again cubic stiffness, but K3 the term corresponding to K3 we introduce an internal variable z bar, which is taken to be governed by this equation. This is the Bouck's model for hysteretic hereditary nonlinearity. So, this P1 and P2 here are taken to be filtered white noise processes, and this we are also adding certain white noises W1, W2, W3 to these 3 equations. These 3 processes can be viewed as modeling errors in developing these Gowning equations. If we have a physical system in mind for which this is an idealization, there will be modeling errors, and we are notionally representing through these 3 white noise processes. So, in this problem therefore, there are 5 white noise processes. We assume that they are all independent, and therefore, we have to recast this into the state space form, and there are some details of the system, parameters here, numerics, which you will need if you want to when you proceed with solving this problem. So, this is the numerical scheme, that is this 1.5 order strong Taylor scheme is this I have provided these details earlier. So, you have to use this, implement this on the given problem. So, if we do this, you will see that here the state space equation will have size 2 plus 2 4 plus 1 5 plus 2 7. So, it is a state space with 7 elements. So, you need to formulate that problem, and once you do that correctly and use this scheme, I have given you the details of the discrete map that you will get when you implement this discretization scheme, and these details you can use to verify if you are progressing correctly according to the proposed scheme. So, these are all details that you would need when you want to solve this. All this are tedious, but conceptually not very difficult to implement. So, you will see that here we have signum functions, and some places we have Dirac delta functions on the right hand side. It is not possible to model events that are captured through Dirac delta function using the discretization scheme that we are using. One possible approach would be to replace Dirac delta function by suitable continuous approximations. For example, we could replace Dirac delta function by a Gaussian density function whose standard deviation goes to 0, and we can use a suitable value for sigma in the numerical calculations and handle these Dirac delta functions. But we could as well ignore the presence of these Dirac delta functions in the actual simulations. but you can account for that through this approximate method. So, I show some trajectories, these are random samples of random processes. So, when you implement this solution, you will not exactly get this because of the variations in sampling. So, this approximately provides you an idea how these samples look like. So, this is u1, u1 dot, u2, u2 dot, and this is the internal variable z of t. This is a sample of p1 of t, and this helps you to see how far your answers would match with, you can check if these are broadly okay. So, this is a fairly long exercise that you need to carefully implement and check. Now, at this juncture we could probably take a global view of what we have been doing in this course. So, this course has been on stochastic structural dynamics. So, the essence of the subject was we will model the uncertainties that are in the loads, in system properties, etc., using theory of probability, random variables and random processes. And consequently, several problems we need to analyze. One is propagation of uncertainty. That means, if there are uncertainties in system properties and excitations, how to characterize the corresponding uncertainties in the system response. So, here we developed analytical procedures for linear time invariant systems, both in time and frequency domains, essentially using principle of superposition, that is Green's function, transfer function, impulse response function, and that type of mathematical tools. We also developed yet another parallel set of tools which are applicable to systems which are driven by white noise or filtered white noise, where the response vector can be modeled as a Markov vector, and consequently several mathematical tools which are based on theory of Markov processes become applicable to solve the problem. Thus, we can study the time evolution of transition probability density function of the response vector using Fokker-Planck equation. We can solve problems in reliability by using backward Kolmogorov equation. We can set up time evolution of response moments, equations for that. We can set up equations for moments of first passage time. So, several tools become available when the problem can be modeled using Markov vector approach. A class of problems are amenable for exact solutions using Markov vector approach. So, Markov vector approach is a source of exact solutions in stochastic structural dynamics. So, it has its own value. Also, it enables us to develop several approximate schemes like closure approximation schemes and certain other numerical procedures which essentially take off from a Markov vector model for the dynamical system. We considered response moments like mean, autocovariance, power spectral density functions, etc. We also considered several indices of system performance like level crossing problem, first passage problem, peaks, envelopes, phase, extreme values, or fractional occupation time, etc. And we developed suitable descriptors for response random processes where these quantities were suitably characterized. For most of these problems, an exact solution was not possible. So, we introduced certain heuristic arguments and developed engineering solutions to the problem on hand. We also considered failures due to first excursion failures where response crosses a safe limit for the first time. Then we also consider the highest response in a given duration, that also helps us to solve the problem of time variant reliability, where we would like to find out over a given duration whether response has stayed within the safe limit or not. We briefly touched upon failure due to accumulation of damage due to fatigue. We used Palmgren minor hypothesis, and also very briefly we also talked about fracture mechanics based approach to treat these problems. The solution strategies, as I said, involved analytical procedures, but also we developed we spent considerable time developing Monte Carlo simulation tools, and we were able to develop procedures to simulate Gaussian or non-Gaussian vector random variables and random processes, completely specified random processes, partially specified random processes, and so on and so forth. And we also developed response analysis procedures for simulating samples of responses. We represented in one class of procedures the random processes as mean square periodic. We assume that random processes are mean square periodic and use Fourier representations for samples. And in the other approach, we used Ito-Taylor's expansion and discretized numerically the governing stochastic differential equations. I also talked about other alternative series representations like Arhunen-Lau expansion for simulating samples of random processes. We addressed an important class of problems known as problems of variance reduction that helps us to reduce the sampling variance in Monte Carlo simulations without increasing sample size. That would typically involve adaptively learning how the system behaves with few simulations and then using that knowledge in finding suitable spaces where we can sample and evaluate quantities of interest. We considered applications, majority of the applications that we considered were in the area of earthquake engineering, and also some applications on fatigue failure was also considered, and a brief reference to statistical energy analysis, that is a framework for studying high frequency vibrations, was also discussed. Now, the question that we can ask now is what next? What are the other with this preparation what we can do and where do we stand in the current state of knowledge in this broad area of research. Now, a few comments I would like to make in the remaining part of this lecture on this issue. The questions that we have considered so far have dealt with the so called forward problems in structural engineering, where inputs were specified, systems were specified, and questions were asked on characterizing the response of the system. But in modern engineering, there are other concerns, like for instance, questions on structural system identification have become important in recent years because of development in sensing and computing technologies. Now, we have instrumented buildings which measure the actions on the structure as well as the corresponding structural responses, and we would like to know the condition of the structure based on these measured actions and responses, and that subject belongs to the study area of structural system identification. This subject is, I mean, in this in the area of structural system identification, we essentially study existing structures. An existing structure can be analyzed using mathematical models and also using experimental tools. So, the prediction from experimental model and mathematical tools often do not agree because of various idealizations, for example, made in mathematical modeling pertaining to boundary conditions, flexibility of joints, constitutive laws, damping models, etc. Typically in mathematical modeling, we make simplifying idealizations in treating these aspects. But in an experimental work, these aspects like boundary condition, joint flexibility, constitutive laws, etc. are depicted correctly. There is no idealization there. So, consequently, the experimental measurements that we make becomes useful tool to update the mathematical models. This updating of mathematical model could be with reference to system parameters such as boundary conditions, stiffness, damping properties, inertial properties, etc. It could also be with reference to reliability models. For example, if we have predicted reliability of a structure to be a certain number, if we make measurements and understand more about the structure, how can that information be assimilated to obtain an updated reliability model. So, this is again an important question that is being considered in recent years. An area of engineering known as structural health monitoring is gaining importance. Here, based on our ability to measure the response of the structure during its operation, we address questions on assessing, for example, whether the structure is damaged, where is the damage, what is the quantum of damage, what is the residual strength or residual life, and these type of questions are being addressed in research as well, and the subject of stochastic structural dynamics forms a important foundation for studying these subjects. Apart from for possible forays into these areas, there are other issues that we could build up upon. For example, most of the applications that we considered in this course have been on problems of earthquake engineering. Similar studies on wind induced vibrations, offshore structures under wave loads, and guideway unevenness, that is automobiles taxiing on rough roads or aircrafts taxiing on uneven runways, etc., could be studied. The same tools, the mathematical tools that we have developed become widely applicable here also, except that we need to now make suitable models for these actions and interface with them with the suitable mathematical tools. Another area where we have not discussed, paid much attention during this course was questions on hazard and risk analysis. So, in all our applications on earthquake engineering, we assume that the event of the earthquake event has already occurred and there is ground motions to which the structure is subjected to. But there is quite a bit of long term uncertainty about the very possibility of occurrence of a earthquake event at a given location during a specified future time interval. So, if these uncertainties are also modeled, then we can talk about the seismic hazard and the seismic risk analysis of engineering structures. Here again the subject of stochastic structural dynamics forms an important component. Studies that I described for earthquake could also be extended to problems in wind engineering. We can talk about hazard and risk analysis of wind loaded structures. Again the tools that we developed in this course become applicable. We have also not discussed issues related to design. Design is an important engineering activity, and the treatment of uncertainties here is again based on probabilistic methods, and there are areas known as performance based design where these tools are primarily important. The design code development, the traditional structural design code development also needs probabilistic background in calibrating the various partial safety factors. I briefly mentioned the relationship between factor of safety and probability of failure, but that line of thinking needs to be developed considerably, and that area takes, this discussion takes us into methods of reliability analysis, code calibration, etc. So, some of these areas could be studied based on what we have learnt in this course. I will briefly now touch upon some issues with the background that we have on these are issues related to condition assessment and health monitoring and so on and so forth. The basic problem here is we need to estimate certain variables based on knowledge of certain other variables which are correlated with the quantity that is of interest to us. So, we will consider some of these problems, and I will quickly illustrate how based on what we have learned we can get a preliminary grasp of the basic questions in this area. So, let us consider a simple problem. Let x and y be two random variables with a known joint probability density function. Assuming that in a particular experiment the random variable y can be measured and takes the value small y, the lowercase y. The question is, what can we say about the corresponding value say this x of the unobservable variable capital X. So, capital X is a hidden variable, and we observe y with a primary interest to understand x. So, the choice of y, which quantity to observe, must be carefully made, and this y should be well correlated with this x, then only we can draw suitable inference about x. Suppose we make an estimate, say x star of the value of x when y equal to y, according to some rule x star is h of y, where h of y is unspecified function of y. The error of estimate here is x minus h of y. We can never hope to make e equal to 0. So, can we select this function h such that we minimize the expected value of some function of this error. So, this is a basic problem in mean square estimation. The same problem can be asked in dealing with random processes. For example, let x of t and y of t be two Gaussian random processes with a known joint probability density function. Let it be assumed that we can observe y of t and not x of t. Given the observation of a sample of y of t for t in 0 to capital T, how to estimate value of x of t for some value of t? This can be this question can be posed in the context of a structural engineering problem. For example, if you are able to measure displacement at a point in the structure when it is acted upon by a load, we may be interested in estimating stress at a point in the structure. The stress itself may not be accessible for measurement at the point where you would like to determine, but we are observing a quantity which is correlated with that. So, based on that knowledge and based on the knowledge of joint probability density function of the quantity being measured and the quantity that is being sought, what can we say about the hidden variable? This joint density function that we are mentioning here as known is known, it could be known in the form of a mathematical model. It could be a finite element model that relates displacement and stresses, and displacement may be measured, and we are asking what could be the stress given that there is a finite element model which relates the two. So, this the knowledge of joint probability density function can come through an elaborate mathematical model. So, we will consider some simple problems so that we get an understanding of what is a basic mathematical issue here. So, let y be a random variable and c be a constant. We wish to estimate y by a constant. This constant is what I can afford to observe, but I want to know what is y. Now, the simple thing is we can find c such that the expected value of y minus c, which is error, and square, so that the signs of the errors are given the same importance, this is minimized. So, E is this, which is actually expected value of y minus c whole square. This is y minus c whole square py of y dy integral minus infinity to plus infinity. Now, we select this c so that dou E by dou c is 0. If we do that, we get the result that this c is expected value of y. So, you want to replace a random variable, you should replace it by its expected value, and that value would minimize the mean square error. Now, a slightly more involved exercise. Let x and y be two random variables. We wish to estimate y by a function c of x. Therefore, the problem is to find c of x such that the expected value of y minus cx whole square is minimized. So, we can write this expression E is this double integral y minus c of x whole square pxy x comma y dx dy. Now, pxy x comma y I write it as product of conditional probability density function of y condition on x equal to x and px of x dx dy. Now, I will reorganize this integral. First, I will carry out integration with respect to y and then with respect to x. Our objective is to minimize E. We can see here that px of x is strictly it is non-negative. Similarly, y minus c of x whole square is non-negative, and consequently this E would be minimum if c of x minimizes this integral, because anyway this is strictly non-negative. So, based on that argument, now we would like to select c of x which minimizes this quantity. Now, based on the solution to the first problem that we solved, where we found out what is the best replacement for a random variable, we get now the solution to this problem, namely c of x is the optimal choice of c of x is conditional expectation of y, that is expected value of y condition on x equal to x. This is the optimal choice. Now, if some remarks can be made, if y is g of x, that means there is a functional relationship between the two. C of x will be expected value of g of x conditioned on x equal to x, which is nothing but g of x, and E becomes 0. If x and y are independent, C of x is y, which is constant. Now, this C of x, if we take it to be a linear function, that is Ax plus b, then we deal with what is known as linear mean square estimation. So, the error of representation is E, which is C of x minus Ax plus b, and the mean square error, average mean square error is expected value of y minus Ax minus b whole square. So, now I select A and B so that dou E by dou B is 0 and dou E by dou A is 0. So, if we first do the calculation with respect to B, we get B to be given by eta y minus A eta x, and now we substitute that into the expression for E and then implement the minimization with respect to A, and we get A to be given by this. These optimal values of A and B, if we now substitute into the expression for the error, this is the error at the optimal point. This error of course is not 0, this is the minimum possible error. So, this is the solution. Now, if x and y are Gaussian, I have not made the assumption that they are Gaussian, you can show that C of x is expected value of y condition on x equal to x turns out to be this. Therefore, for normal random variables we can see that these two answers match. Therefore, for normal random variables linear and nonlinear mean square estimation lead to identical results. We enunciate what is known as an orthogonality principle. This expected value of mean square error is given by this, and the condition dou E by dou A equal to 0 would lead us to the condition that expected value of the term inside this brace, which is y minus Ax plus b into x is 0. Now, we can see that this term inside the brace, here is the error, this is error of approximation, and x is the observations, we call it as data. So, what is said is x is according to this rule, this random variable which is y minus Ax plus b is orthogonal to x. Two random variables are said to be orthogonal to each other if the expectation of their product is 0. Now, based on that we say that data is orthogonal to the error. Now, we can generalize the formulation to a set of n random variables. So, let S be a random variable and S hat be an estimator of S, that is A1 x1 plus A2 x2 and so on and so forth. This I can write as A transpose x. Now, how to select A1, A2, A3, An so that this capital P is now the error is minimized with respect to AIs. So, how to select AIs so that dou P by dou AI is 0 for I equal to 1 to n. So, this can be done, we have to differentiate with respect to A1, A2, A3, An separately and put the error to be 0, and this leads to this matrix equation where Rij is expected value of xi into xj. So, based on that we can get the value of the constant that we are looking for. We can make some more observations. We have S minus S hat into xi, this is the error into this data is 0 according to the principle that we talked just now. So, if we simplify this again we can show that S minus S hat is orthogonal to S hat. So, based on that if we utilize this result we can actually find out the optimal value of the error, and that error turns out to be this quantity. So, this can be verified. We can extend this for problems of nonlinear estimation where we estimate S through a nonlinear function of x1, x2, xn, which is g of x1, x2, xn. So, the error of replacement is again S minus g, and the P is expected value of S minus g whole square, which is this, and we again split write this joint density function in terms of a conditional probability density function and a joint density function of x tilde, and we again notice rewrite this as follows, and we notice that this is positive and this terms inside the brace is positive. Therefore, the way to select g is to minimize this inner integral, and based on that we again get this result that this nonlinear estimation also tells us that this should be expected value of S condition on x tilde is equal to lowercase x tilde. The generalization of orthogonality principle, we showed that data is orthogonal to the error. We can also show that data is orthogonal to a linear combination of the linear combination of data is orthogonal to the error. This also can be shown using the result that we have. Now this is a small exercise. If g of x is a nonlinear mean square estimator of S, the estimation error S minus of g of x is orthogonal to any function w of x, linear or nonlinear of the data. So this proof I have developed here again follows the same logic that we have used so far. We write the expression for this expected value of S minus g of x into the function of this data and rewrite this joint density function in terms of product of a conditional density and a marginal density, and again notice certain features of the response, and we reach the conclusion that S minus g of x is orthogonal to w of x. In fact, if S and x are jointly normal, it can be shown that linear and nonlinear estimations of S are equal. This you can do as an exercise. Now we have talked about random variables. How about random processes? Let S of t and x of psi be two random processes where psi takes values from a to b. Now we consider the problem of estimating S of t for a fixed value of t in terms of x of psi specified for every value of psi in an interval a to b. So that means x of psi is the data available. In the example that I mentioned, x of psi is the data on say the strain or the displacement that you have measured, and this S of t is some response quantity of interest which is not measured. So what we do is, generalizing the linear estimation problem, we assume we propose a estimator S hat of t is a linear function of the data a to b x of alpha h of alpha into d alpha. This function h of alpha is not known. Now we need to select h of alpha such that this p is minimum. Now if we discretize this integral as a summation like a Riemann sum, we have the solution already with us for that, and on that we can take the limits. If we do that, we get the equation for h of alpha k, which is given here, and then if we now take the limit of delta alpha going to 0, we get this integral equation where h of alpha is buried here. Now if the time at which we want to find S of t is within the interval a to b, then we call this problem as smoothing. If this t does not belong to the observation time interval, either t is greater than b or t is less than a, we call it as a problem of prediction. Filtering is of course the case where x of t is not equal to S of t. So these are the terms that are used in estimation theory. So we will consider some simple examples. Let S of t be a stationary random process. Estimate S of t plus alpha in terms of S of t. That is a problem. So what I do? I assume S hat of t plus lambda as a into S of t. So the error of this representation, the expected value of the mean square error is p, which is given here, and if I now minimize p with respect to a, I get a to be this. So the optimal estimator for S of t plus lambda is a into S of t, where a is given by this, and the corresponding error, that is optimal error, you can show that for a specific choice of RSS of tau, it is shown here, you can verify this result. Now this is a slight variation. What here we will do here, what we will do here is, we will assume that S hat of t plus lambda is a linear combination of S of t and S dot of t. Suppose we have made observation on S of t as well as S dot of t, it will be a1 S of t plus a2 S dot of t. Now we note that S of t plus lambda minus a1 S of t minus a2 S dot of t is orthogonal to S of t and S dot of t, and S of t and S dot of t, S of t is taken to be stationary. So the process and its derivative are uncorrelated at the same time instant. So again we formulate the expected mean square error, minimize with respect to a1 and a2, and if we carry out this, we get a2 and a1. So this estimator is something that you have to design, and the error actually between two possible estimators, there will be different errors. So you can compare them and make further choices. So this is the optimal error in this particular case. Now, filtering problem, we estimate S of t, S hat of t is A into x of t. So, again P is this, minimize with respect to A, we get A to be this, and this is the optimal error. We can consider further problems like problem of interpolation, where the problem is to estimate S of t plus lambda, that means somewhere here this value we do not know, we are not observed, in terms of samples of S of t at these discrete time instants. So, this problem is used for example in developing structural matrices in stochastic finite element method, where these are the nodes and we interpolate the random fields within the nodes using this logic that we are discussing. That is one of the tools that is used in stochastic finite element methods. So, what we do is the estimator S tilde of t plus lambda is taken to be a linear combination of what has been observed, and again if we minimize the mean square error of this representation, we get equations for these AKs, which are actually a set of 2n plus 1 equations for these unknown constants, and that can be they will be in terms of known properties of S of t and they can be determined. The problem can be extended to problems of quadrature. Suppose you want to find z which is 0 to b S of t dt. So, what I will do in estimator for z is a linear combination of S of t evaluated at certain time instance 0, capital T, 2t, 3t and capital N t. So, we can implement this method and we can derive these a naught, a1, an and we will get n plus 1 equations by minimizing the mean square error with respect to these AKs, and this problem also affords a approximate solution. How about a problem in smoothing? We estimate the present value of S of t in terms of values of x of psi for psi varying from say minus infinity to plus infinity. So, x of t is S of t plus some noise, S hat of t is some output of a, I mean we are convolving x of t with a filter and this filter has to be determined. The transfer function for the filter has to be determined, and the same if you use now the orthogonality principle, which is reflection of the criteria of minimizing mean square error, we get this equation which is an integral equation for this filter, which can be used for solving this type of problems. Now, I will close this discussion by making a quick reference to the basic problem of dynamic state estimation. So, in the discussion that I described we went through just now, the joint densities that we are talking about were assumed to be known, but I already mentioned that knowledge may come through a mathematical model. So, suppose we are interested in the process equation which is obtained by a mathematical model, xk plus 1 is phi k xk plus wk. Then the measurement is on another quantity zk, which is measured quantity is a linear transformation on the states. Now, the basic problem here is this process equation can come through, for example, finite element modeling in structural engineering application. This comes through our sensors. So, the problem on hand is that we need to find out the posterior density function of the response vector given that we have made these measurements. This is joint density function between x0 k is the vector x0, x1, x2, xk. So, this is actually the posterior joint density function. We can take the kth instantaneous state and consider probability density of xk conditioned on measurements up to that point, and this is known as filtering probability density function. Alternatively, we can find the expected values, conditional expected values and the conditional covariance. In problems of condition assessment, structural system identification, the determination of these quantities are of fundamental interest, and there are various tools such as Kalman filters and particle filters etc., which are designed to answer questions of this kind, and that become quite useful for solving, as I said, problems of system identification, control etc. So, this gives a glimpse of the application of the topics that we have studied in the course. So, based on the topics that we have learnt in this course, you can probably now study say area subjects of structural system identification, dynamical system control theory, etc. So, at this juncture we will close this lecture, and this course also closes at this point.